Hello everyone, this is Professor Yu. I'm going to talk to you about how to solve the discussion problem for week 3 of Chemistry 1. This is a week 3 discussion problem. First topic is electron configuration. So, electron configuration. So how the electrons are being filled up in different kinds of orbital. So that's number 1. And state the electron configurations. That's the one, and then they ask whether it's diamagnetic or paramagnetic. Okay. And the last one is which is isoelectronic to. So find out what is a neutral atom to isoelectronic to the following ionic species. So electron configuration, you need to refresh your memories on how the electrons are filling up the spaces. The orbital we call, and then the useful diagram is something looks like this: 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. So this is how the principal quantum number and the L, the angular momentum quantum numbers, angular quantum numbers are being filled up, and we call s orbital and p orbital, and they are allowed to state, and then we can do that. And the 5 s's here, 5p, 5d, and so on, and even 6 s's, and then you can so on. And then the way that this is being filled up, you might remember these kind of sliding arrows. This is how. Okay, so 1s, 2s, 2p, 3s, 3p, and 4s, 3d, 4p, 5s, and this one 5d, 5p, and 6s. And so this is how things are being filled up here. So if I write it down on the piece of paper here, 1s, 2s, 2p, 3s, 3p, 4s, and then it's a 3D, and then the 4P, the 5S, and then the 4D. So this is a sequence how it looks like. And it's actually a good idea for you to relate this with a periodic table. 1S, 2S, and 2P are related here. This is a 1S, 2S, and then this is a 2s, this is a 2p, this is a 1s, and then what comes next? 3s, so this is a 3s, and then this is a 3p. So far so good. I mean, we are filling it up as we go on. The next one is 4s, right there, this is a 4s, and then this one, we might want to color it in a different color. So this one right here, although it is located, so this is how the electrons are being filled up, just like we write it here, right? But this is now for 3D. So this is actually 3D orbitals, and then the 4p orbital, which is shown up here, right? 4p orbital shown up there is this one. So let me be consistent with the color. So this one is 4p, and then this one is 5s. So right, so this is a 5s, and then you need to use you need to fill up the 4d comes next. So that is actually ends it up as a 4d. You know, if you guys can continue to do this, 4d, 5p, right? So this is how 5 P's are being filled up, and this is a 6s, and this is a 1 is actually expanded upon, and that's why after 6s, where does it go? It goes here, right? It goes this is a 4f, and then this one is that's why you have a bunch of things here, and then the rest of them is going to be filled up to have, I guess, 4D, 5P, 4D, 4F, and then I think that I made a mistake here. This should be a 5, right? So this is a 5D, and then this is a 6P, right? So this is getting a little bit more complicated, but it's really at the starting point is 1S, 2S, 2P, 3S and 3P, and then this is where the periodic table, how this is being filled out. And then the important column here is the new halogen column that is completely filled up on. So okay, so let's solve the aluminum here. Thanks for this is a little more background that probably I need to cover to you. Aluminum here is number 13. So number 13 aluminum has the same. You need to go back and then to find out the number of. It has 13 electrons. Okay, so aluminum has 13 electrons, and this one is essentially same number as a neon, and then you have 3 more electron. That's from the 3S, and then you have one electron in 3P. So that's how I can write. What about the aluminum 3+? That's 10 electrons. So this is 10 electrons. So that one, therefore, it has the same number of electrons as a neon. Okay, so that's what they are. What about the sulfur? Sulfur is the one that shown right here. That's a 16. So sulfur is a Z is 16, and if it's the same as essentially, I can show it in a different way. That is a 10 electron plus 6 more electrons, and 10 electron means neon, and then you have a 6 more electron, which is fill up 2 electron in 3S, and you have to fill up 4 electrons right there up to in the 3P. So 3S2, 3P4. So that's how I want to write. And then S2 2 minus means you have a 16 plus 2 more electron, 18 electrons that you have. So therefore, this one is actually going 1 more electron and then 1 more. So it will be isoelectronic to argon. Okay, and the last one is this ion. This is probably will be discussed in detail. So I'm going to let's use a bottom space here. Okay, so let's look at the ion versus ion 3+. So ion is located, where are you? Yeah, right here, number 26. So ion is number 26. And then this one is the closest but fewer number of electrons of noble gases is an argon. So you have an argon. Argon means this one is 18 electrons, and the rest of them is 8 more electrons. So how the 8 more electrons are being used from the argon, you need to fill up here. That's 4s2, and then 1, 2, 3, 4, 5, 6. So that's 6 electron in 3d orbitals. So 3d orbital, you have 6 electrons. Okay, so that's where you're looking at now. And then now we're looking at the situation that we are losing 26 minus 3 electrons, so that you can be 23 electrons, and this is a scenario. So now the question is really, this is where you have an electron before, and which electron do you want to lose? And then I am going to draw you the orbitals. So this is a 4s orbitals, and then 1, 2, 3, 4, 5. This is a 3d orbitals shown up here, and you have up and down 1, 2, 3, 4, 5 electrons, and one more. So that's why 4s2 and 3d6. And from here, I need to lose 3 electrons. I need to lose 3 electrons here. And which one electron do I lose? And you have to looking at the electron pairing situation. That is important when you're looking at, particularly actually the d orbitals involved. And so looking at here, first electron that I'm going to lose is more likely the one shown up here. This electron will be lost, and so therefore, after losing that electron, so first electron after losing it, you will have a 5, like everything paired up. So there is a kind of the pairing maximization effect. This is a synergistic, and they prefer to be that way. This is a D5 state, and this is a really make this is a favorable state. So they would like this state very good. So first electron, they will need to lose it. And then what else do they lose it? They're going to lose these 2 electrons. So they're going to lose 3 electrons this way, because they want to keep this the D5 unpaired electron paired up state. So this is a 3-5, and then they simply has no electrons left. So therefore, to know this, Fe3 plus is isoelectronic to argon, okay, which is 8 electron, and then the 3d5 electrons. So this is a case where they can keep it up. As a side note, you might remember the iron oxide is Fe2O3, and this is the rust, the iron oxide, and that's where because oxygen is 2 minus, therefore you prefer to be iron is 3 plus, and this is one of the favorite state because they can really maintain the synergy of having d orbital all paired up and this have an unpaired electron fully occupied. So it is one of the nicely paired up state. There is a nice interaction. They want to keep it that way. Okay, so that's what we say that about the electronic state, electronic configuration. So this is about ions, and this is about ion 3 plus. And then they're asking that which is on diamagnetic and the paramagnetic. So dia means you have no interaction with the magnetic field, and the electronic sense orbital, you have everything electrons are paired up, whereas a paramagnetic, as long as you have an unpaired electron, it is like a little spin with a current, so that has a magnetic moment is still there. Okay, so those which is a diamagnetic, that's and the paramagnetic. So let's look at this argon here. This is because of this one, that's a p orbital with a 1 electron. So this is a paramagnetic. Okay, so this is a para. And when after losing 3 electron, everything is just like a neon. This is a diamagnetic. Right? Okay. What about the sulfur? Sulfur itself is a neon plus this, and this is all paired up. So that one itself is like a diamagnetic, but the p orbital, 3 orbital, 1, 2, 3, and 4. So because of 2 electrons are unpaired up, this is a paramagnetic. Okay. And paramagnetic is, I'm going to circle it. Okay. And what about the S2 minus? S2 minus, just like an argon, everything is paired up. Argon, in a way, argon is 1s2, 2s2, 2p6, 3s2, 3p6, right? All the orbitals have even numbers and all paired up, completely filled up electrons, so that's a diamagnetic. What about the ion itself? Ion itself, you saw here and already draw the diagram, and this is an unpaired electron, so therefore this is a paramagnetic. And Fe3 plus, like I said, this is an Fe3 plus orbital diagram that how electrons are being filled up, so this is also paramagnetic. Okay, So this is how I solve it. The last question is, can you find what is a neutral atom that is isoelectronic, means the same number of electrons to Al3+. So Al3+ is a number of electron is 13 electron as a neutral, and you're losing 3 electrons. So that means a 10 electron neutral molecule. That will be the one shown up here. You see the 10 neon. Okay, so that will be a 10 neon. Is an answer. The number 2, S2 minus. I saw that before. That's S is a 16, and then you need to have a 2 minus, so 2 more electron, 18 electron total. That is same as argon here. So this is therefore this is an argon. Okay, so that's a neutral atom that is isoelectronic to S2 minus. Okay, so we have covered the electron configuration, how this is being filled up the space, and this diagram, and I was trying to relate that with the periodic table, how this is being solved out here. And it is pretty much the good practice, and you need to refresh your memories about 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Okay, so this is the first row, and this is second row, and this is the third row, and this is the fourth row that is shown up here, right? So first row right here, second row 2s2p, third row 3s3p, and the fourth one, which is a 4s 3d and the 3p. Okay, so that's how the electron configuration energy levels for single atom electrons are going to fill up. Thank you.